Good morning, everyone, and welcome. My name is ÓSCAR, and today I'm going to talk about basic notions and first steps with big data. Just to start with, so I'm not so nervous, I'm going just to talk about myself, but it's a bit easier just to start like this. So I am from Spain, and I come from a city that is in the center of Spain, in Madrid. And I'm a telecommunications engineer, and I did my studies in Madrid, and I finished in a small town called Lund in Sweden. And then after I finished my telecommunications engineer, I did a PhD on computer science, and I was very lucky to have an internship of the Spanish government, and I did my PhD between Madrid, Sydney, and I guess this is the reason why I'm here, Buffalo, New York. And just to give you a background of how I started to be a researcher, I started doing research with how signals are transmitted from A to B, and specifically how to compress these signals. So they are compressed when you speak on the mobile phone, they are transmitted, and how this compressed signal is completely recreated when it comes or whenever you arrive to the receiver. And for my PhD, I worked in the area of artificial intelligence and machine learning, and basically with videos and human activity recognition. So trying to figure out what people were doing in videos. It was the years that all the video surveillance systems were very demanded, I guess, after the 9/11 and all these things. So currently, I work for the Center for Big Data Research in Health at UNSW, and I'm still using artificial intelligence and machine learning and big data, that is the topic of today, but mostly for better patient outcomes, or to improve patient outcomes, and to improve the processes of the healthcare system here in Australia. So I'm also one of the founding members of the Spanish Researchers in Australia Pacific that they are the host today. So thank you very much to the association. And I just wanted to say that the association is a wonderful opportunity for us expats to show a bit of what is the knowledge that we're bringing from Spain here, and also for Australians to know a bit of Spain in this aspect of science. And also, I think I'm very grateful to my country because our education system, I think it's very good. So I'm coming from a middle-aged, not middle-aged, sorry, middle class. And all our educational system is for free. So I think I'm very lucky to have gone to public schools, public high schools, and ultimately to public university. I think that's something that we take for granted in Spain, but I think it's very, very, very important to have this public system that allows everyone to have this education. So in a way, I want to give something back to my country because I'm grateful for that. But this association has allowed me to do that. And not only that, we have a wonderful time every time that we meet. So it's also the social component and things like that. So basically for this workshop, I divided the workshop in two parts. And the word workshop in 1 hour, maybe we can't do anything hands-on, but I would like you to interrupt me, ask any questions, and participate as well. So that's the idea of workshop. Well, so in a way, I would like to establish a dialogue. So don't hesitate to ask me any question. Many of the examples that I'm going to give are health, because it's the area in which I work now, but they can be extrapolated to any other area. So I'm going to start with this slide, just so we know, or we have an idea of, I don't know how to take this away, of what big data is, and this is just live stats that are happening right now. So basically, what is happening on the internet, or what is happening in the internet today. So these are the amount of emails that have been sent today. So 95 almost 96,000 million emails have been sent today. How many Google searches? Well, it's almost 2,800,000. Number of tweets, so far 300 million, but we will see that the average in a day is 700 million. The number of videos in YouTube, I mean, it's just these numbers are just amazing. I mean, they're so big. So this is data that is being generated just today as we speak. So, and that many of that data is generated just by us, you know, by users. So they are not only companies and other entities. So I'm going to leave this just there. And then the first part of this presentation was, you know, I was wondering, like, how did we get to this point? How did we arrive to this point in which we have these tremendous numbers of data being generated? So I'm going just to tell a little story. I hope to be brief. And as I said, interrupt me if you have any question. So first, like, we know how data give us power. And I started with this, I found this on the Wikipedia, and it's the first civilization in Babylonia and the Sumerian Empire. They already had the first written documents, and in this case, it's just a census. So that was around 4,000 BC. So as you can imagine, the person that had this data, they know who lived in their empire or in their kingdom, so they can collect taxes. They know how many people they have. So this information is giving some kind of power to that person. At the same time, the Egyptians, this is something that was found quite recently, 4,500 years ago, I think, and it was a ledger of the construction of the pyramids. So basically, everyone that was working there, how many portions of rations of food. So everything was recorded in this ledger. So basically, this gives you an idea of how much food you need, how many materials. It could be reusable to build another pyramid. So this was for building one of the pyramids. And then more recently, by the way, Jorge, do you know how I can get rid of this? Because it's a bit annoying.
Hide floating screen, I think. It's on the orange bit, and then go down.
Where?
Hide it down.
Perfect. Yeah, I'm talking about big data.
That's a small data.
Yeah. And this is more recently, the Crimean War. If you remember, the Ottoman Empire declared war to Russia because the excuse was that Russia wanted to take care of the Christians that they were living in the Ottoman Empire. So France and the United Kingdom allied with the Ottoman Empire. And in this case, Britain sent a lot of troops to Turkey to fight against the Russians. So despite the fact that the Crimean War lasted only 18 months, many soldiers died while at the front, while they were at the fighting. And then this woman, Florence Nightingale, she was a nurse that she was sent to the front to take care of the troops. And she realized that the hygienic conditions of the soldiers were really bad. And she started to collect data of the reason why people were dying. And she started to not only to collect data, but to create graphs. So perhaps one of the first graphs that were created in history. This is a bar chart in a way. So what you can see in blue are the deaths of people that they were dying of preventable diseases, and mostly were contaminated water or lack of hygiene. And the red or the pink bars are people that, or soldiers that died directly of wounded, provoked by weapons. So she proved that preventable diseases, just potable water, for example, was very important so people didn't die. So when she went back to the United Kingdom, she showed this to the Royal Commission and things changed. So from then on, the hygienic conditions of the troops were very different and not so many people died. And not only that, but Florence was the first woman in the Royal Statistical Society. And she pushed so much for that hospitals started to collect data systematically about what is going on in the hospital since then, thanks to her. And also she was a great advocate for public healthcare system. So it was the beginning of the NHS. And also as the profession of nursing, she was the first one that professionalized and created a faculty in King's College London. So data could be very powerful, as you can see. And then I want to just remind you all, and I think everyone here knows about old-fashioned data. You know, that's not fancy anymore, but still we have paper-based data. I mean, everything that we have here, you know, books, newspapers, letters, registries. And the thing is just that we only talk about big data, but we don't have to forget that still nowadays, many of the data that we use is paper-based. For example, in hospital, not everything is electronic. So we have a lot of health records that are still paper-based. So don't forget that, because still we are in the transition, but still we are using a lot of paper-based. And also we have all the analog data that we have been collecting during years. And you always, I mean, of course you remember the videotapes, the cassettes, the vinyl. So in a way, this digitalization of this change to big data has happened quite recently. So how did we go from here to where we are now? So what happened? What was the transition? Any ideas in the public? What was it that created this transition, or that prompted this? Do you have any idea? Internet, yeah. I think internet was a great vehicle for digitalization and creating new data. Any other thought? Computers. Anyway, I'm not creating more tension. Yes, I mean, so we have what people call the digital revolution, or the third industrial revolution. And basically is this shift from paper and from all these formats, cassettes, videotapes, to electronic technology or to digital technology. So this already started happening in the half of the 20th century. So I think everyone here remember the old days. And then I just thought of 5 pillars that took us from where we were to where we are now. And I'm going to go one by one, but basically 2 of them you already mentioned them. So the first one is computers. So a computer, and this definition is taken from Wikipedia, is a machine that can be instructed to carry out sequences of arithmetic or logical operations automatically via computer programming. So basically, we know that a computer is able to do many operations and many logistic operations. Basically, you know, it's a general machine that helps us to do many things today. But I just want to put the attention that at the very beginning, computers were only conceived as calculators, as calculating devices. And the first computers were not even digital, they were analog computers. So the first computer was created in 1872 by a man called Sir William Thomson, in the United Kingdom, and it was a tide predicting machine. So basically, Sir William Thomson realized that in order to predict the tides were periodical, or they were governed by this equation. So basically, this equation was a trigonometric equation, and I just put there 3 terms, but I have like 11, I think it is. And this computer, this analog computer, was just solving this equation in order to predict the time at a specific time t. So very different to the computers that we know today. That was pillar number one. Pillar number two, I think, is digitalization. I mean, what happened that that we used to have analog signals, and by analog signals, for example, this is the black and white TV signal. So basically what I mean is just that it's a continuous signal that could go from 0 volts to the maximum could be, I don't know, 10 volts or something like that. And then it could have very strange shapes, and it has to be transmitted, like for example, if it's television, it has to be transmitted via antennas for television, but if it was a radio signal, it's just you have your radio signals, electromagnetic, so every device has their own receiver and operator. So for example, if we want to add color, we have to add all these spikes there. So this is the color TV. And obviously it's very different to the simplicity of what is just a digital or a binary signal, which we all have ones and zeros. So it's much easier to transmit. And I was telling Manel that it is binary, it's 1 or 0, because basically it's very easy. We could have chosen three levels instead of 1 and 0. It could be 1, 0, and 2. But the simplicity of only having 2 levels is that it's much easier to distinguish. Either you have a 0, which is 0 volts, or you have a 1, which is 5 volts. So that's very easy to distinguish versus if you have 3 levels, you have more, you know, it's a bit more complicated. So just a bit more of digitalization. It's just that we have a binary system. As I was telling you, everything is expressed, everything, all the information is expressed as just zeros or ones. So as an example, for example, let's go into see how do we code number 89. So as you can see there, the position of where we have a 1 and a 0 is very important. So the position to the right-hand side, the most right-hand side, is, I mean, everything is a power of 2. So if we have a 1, we are going to take into account this power of 2. If we have a 0, that will be a 0. So I explain myself. For example, number 89 will be that 0, 1, 0, 1, 1, 0, 0, 1. So if we have 1, 1, oh, I have a mouse. I can go here and say with the mouse. Yeah. So because we have a 1 here, we are going to have 2 elevated power of 0. Anything that is power of 0 is always 1 mathematically. So this will be 1, 1. Because here we have a 0, this will be 0. 0 will be 0. And here we have a 1. So this will be 2 to the power of 3. So 2 power of 0, 2 power of 1, 2 power of 2, 2 power of 3. 2 power of 3 is 2 times 2 times 2, so 8. And then we have number 8 here. Because we have a 1 here, this is 2 power of 4, so we have 16, and so on. So when we sum this number, we will have number 89. And all the numbers are coded like this in binary. It's a very easy way to code any number in the world. Is it clear? This is fascinating. But in this case, we have the agreement that we are going to code numbers. But we can have the agreement that instead of a number, this could be a letter. So for example, fine, this is the number 111, but we can make that this representation is the number, the letter lowercase o. And this is what we do with the keyboard. So basically with this, we have the ASCII, which is how we code our all our letters, capital letters and lowercase letters, just with numbers. So basically this is what we do, and how every time we press a letter, we are sending these bits to the computer. This is the original ASCII, that it was only English, and because we have some Spanish audience, just to see that ASCII was extended. And then we have our accents, and the letter ñ, and the question mark at the beginning, and the exclamation mark at the beginning. And basically, this complicated signal that I show you with the TV, that it was like, for example, this blue one, can be in a way sent in digital form by approximating the signal with the red one. So basically, if we have, for example, 3 bits, we can code all these signals in these different levels and just transmit, for example, for this part, we just transmit 1, 0, 0. Then if we want to, I'm going to transmit this other part, 1, 0, 1. So every signal, as you can see, depending on how many bits we have, in this case, for example, if we only have 2 bits, we only can express 4 levels. With 2 bits, we can code number 0, number 1, number 2, and number 3. So this is, in a way, the more bits you have, the more accurate you are representing signals. That's why when we have computers with 64 bits, they are much better than those ones that have less bits, for example. Okay, and then this digitalization goes even further in the way that we can create, like with these bits, some basic operations, very basic operations. And in this case, 3 operations. This is the basic of all the mathematical operations that we do in the computer. This is like a Lego game, and these are the bricks. The bricks are 3 operations that are called and, or not. And with these, we are able to replicate all the mathematical operations that we have in the world. So basically, the AND operation is just that if we have this operation that is AND, it's just that if we have bits that are, if we have something different to 2 ones, in this case, is we have 2 bits. So if the 2 bits are 1, the result is 1. Otherwise, it will be 0. The operation OR, what it says, and this comes from algebra, means that if we have 2 zeros, the result will be 0. If there is a 1 included here, the result will be 1. And the NOT is just the opposite. If the input is 0, the output will be 1. And if the input is 1, the output will be 0. So just to translate this into examples, how we can translate the AND operation or the OR operation to NOT to things that we understand. Imagine that you are on the internet and you want to find videos of puppies and kittens. If you are using the AND, imagine that X is puppy and Y is kitten. So if you say on the internet, I want a video with a puppy and a kitten. So that means that both terms have to be 1, and the video has to have a puppy and a kitten. Or you can use the OR, which means I want a video with either a puppy or a kitten. So then the video can have only a puppy or only a kitten or both. Or you can say not. I mean, I don't want videos with kittens, just puppies. So basically, you just have a video with a puppy. So basically, these are the bricks that allow us to create any mathematical operation. And these are called gates or logic gates, and they are representing with these little plots. And the marvelous thing that happened in 1940s is that this man, Claude Shannon, he was an electrical engineer. And he realized something very, very clever and very intelligent. He said, oh my God, you know, if I have an electric circuit, because he was working as a telecommunication engineer, he said, you can simulate these operations just with switches. You know, he was working for a telephone exchange. If you switch it on, this is a number 1. If you switch it off, this is a number 0. And then he said, there is a parallelism between this algebra and an electric circuit. So then, because this algebra is like the founding bricks of everything, he said, okay, I can do this with little chips or with little components. And well, anyway, I'm not going to go here, but basically it's very easy to create. This is a NOT gate. So you can go to an electric shop and just buy the components. You can buy what is called a transistor, and the transistor is just a semiconductor that simulates a switch. And then you go there, and it's this one with the three little legs, 2 resistance, battery. You have a NOT gate, and this is how it was done in the old days. And this is what we used to do in the faculty, by the way. But not only that, but big circuits. And basically, with these little gates, you can start creating, as I was telling you, little blocks, little by little. For example, this one is just how to, if we have two numbers, how we sum them. This is number 3, and as I was telling you, it could be expressed in binary, like 0, 0, 1, 1, and this is number 9. So the result, we know that it's number 12. And then we know that number 12 is coded like this. So if we want to sum this, 1 plus 1 here has to give 0 because this is a 0, but then we have to carry 1. Okay, we are going to design this with these gates that I was telling you before, and in this case is 2 gates, one that is an AND and a NOT. But you don't have to worry about it. All I'm telling you is just that if you have 0, 0, 0, 1, or 1, 0 in these inputs, the result will be a 1. If you have 2 1s, it will be a 0. So let's go into sum just 2 numbers, the last 2 digits of these binary numbers. So if we go here, we know that this is number 1, and this is big 1 and big 1. So big 1 and big 1. And when we have 2 1s, the result is going to be a 0. So here we have a 0. Then we know in this that we have a 1 because A here is a 1. So 1 and 0 is going to give me 1. So here I have a 1. Then if I take this, where's the next one? Okay, B is also 1. So 0 and 1 will be 1 because 0 and 1 is 1. So the sum here, that here will be 0, 1 and 1 is 0. There you go, 0. And now let's go on to do the carry. So the carry will be this 0 come here in the circuit. So it's there. And 1 and 0 will be 1. So the carry will be 1. So this is how to just sum 2 bits. But if we put it all together in this circuit, we have how to sum 4 bits. And this is how computers, with these little operations that I told you, and, or, and not, produce all these things. And then now you don't have to go and buy the components one by one. You can buy this microchip. But what we ultimately have in our computer is something like this, all these chips, microchips, sorry. Okay, and this is super revolutionary because if you think about it, communication until the 1950s was thought of just, you have to send electromagnetic signals. The idea that you can send zeros and ones, and in this case, because Sharon established the parallelism between 1, 5 volts, 0, 0 volts, is amazing because you can now unite all the signals into just zeros and ones, whereas before you have different devices for different signals. So there is a digital revolution, basically, and it's very easy to move media from A to B. So basically, just to repeat this, in the old days, the telephone has the telephone signals to the telephone wires, the camera, you have your camera, and you have to go to the shop and you have to buy the film. If you have television, you have to have a television with the receptor, with the antenna. Now everything is the same medium, if you want to put it that way, because we have digitalized everything and we are sending 1 and zeros. So basically that's why we have the internet, and we can call over the internet, send pictures over the internet, do basically everything over the internet thanks to this digitalization. Okay, this is pillar number 2 that I think my my telecommunications engineering background made me be to stay there a lot. But another thing is that has been amazing is hardware, how hardware has changed in the last year. So only from 1990 to 2010, the speed of the central processing unit, CPUs, sorry, central processing unit, grew by 5,000. And if you see the speed of these microchips that I was showing to you before, these microchips, it's been growing and growing and growing. And so we are, this is 2016, so it's still going up. And this is the number of transistors. Remember these transistors, that were these switches that I was telling you, that you can put into a microchip. And this is the Moore's law that says that every year, the amount of transistors that you include inside a microchip basically doubles. And that's been going on since 1970. And okay, well, at the beginning, you double 1,000 to 2,000, but then when we are here, we are doubling, you know, 50, 100 million to 1 million. And this has been increasing non-stop. And funnily enough, now as we speak, we are arriving at a plateau. So it's not growing exponentially as it used to grow. So now we are in a plateau because it's so little that we have to become with new technologies in order to continue with the Moore's law. So basically, hardware has played also a big role in why we have this big data. And as you were saying, I think a big player, or pillar number 4, is the internet. Okay, so far, everyone, imagine you are generating your pictures and everything, and you have it in your computer, in your PC, or in your camera, or in your device. But now, all of a sudden, we are connected. Everyone is connected. And I'm always thinking, for example, in a hospital, you know, like if you are in one hospital and you are recording electronic data, you have the internet and you can send this to a device that is far away. And everyone basically, because I spoke of computers at the beginning, but now a mobile phone is a computer as well. So we are generating all this data. And then not only that, we have the concept of Internet of Things. Do you know what the Internet of Things is? Have you heard of it? What is it? Sorry, to connect?
To connect devices.
Yeah, what kind of devices? So the use of Internet to...
So from a fridge to
you name it. Exactly. So now we are at a point, and again, because of this magical thing of digitalization, that every single thing, even if it's a chair, could transmit, you know, like your fridge, the temperature, the, you know, what kind of food you have, I don't know. But everything could be connected to the internet. My phone now, you know, like moving and probably saying, oh, what is Oscar doing, you know, with his hands. So this is generating an amount of data that is huge. And then another thing that the internet allowed that I think is fascinating is just that before we have to, or we used to store everything in our computers, but now everything is in the cloud. So we have companies like Amazon Web Services, or Microsoft with Azure, and then, you know, everything, all our data is living in those servers. So then again, we don't have any limitation with data. Like for example, here at UNSW where I work, we have everything on Microsoft computer. So all my data is in the cloud. I don't even if I have my computer. So I think the internet has accelerated this big data story. And then I think also software in the sense that, okay, we have the hardware that I was telling you, we have the switches and the gates. And then how do we talk to the machine? You know, we have what we call machine language, which is basically code 0s and 1s, just bits, 0s and 1s. And then on top of that, someone created what is called assembly language. An assembly language is very simple. I don't remember how many instructions it has. It's something here, but it's like, move this to this part of the memory, or sum these two numbers. So basically, this is not the logic gates that I was telling you, the and, or, and not. It's a bit more sophisticated, but it's still very primitive. And then on top of that, someone created high-level languages. That is what it allows us to create, like, for example, similar to as we do in Excel, that we have, if the price is bigger than 10, then do this. So this is a language that is high level, that is talking to the machine at the very end into 0s and 1s, but it allows us to abstract, to do some level of abstraction. And then it went all the operating systems. The first one was MS-DOS. I think you say it like this in English, and Windows. And then we have even more high-level languages like Python that we use today for machine learning, or Java. And then at the very top, we have these apps that everybody uses, you know, like the applications with the iPhone and things like that. So far, so good, everyone? Are you super excited with this? Any questions?
What's Scratch?
Scratch is, I mean, it's just because I took this from the internet. It's a language that MIT in the US came up with, and it's a very basic language for mostly for children to start learning programming. So it has a lot of drag and drop, is that right?
It's like a visual language, but you can like pieces together, like
Yeah.
a puzzle. Yeah, you make like
Exactly. So you don't even have to type anymore. And we can see the website later, but it's very cute with little cartoons. And it seems like the ABC kids, you know. So it's a bit like that. Okay, I'll show it to you later. Okay, and another thing that I think is fascinating is the open source. So basically, in the last years, I remember when I was a student in the 1990s, this wasn't so big. But now, you know, my students, I teach machine learning at UNSW. It's amazing, you know, you have a question and like, and you know, and sometimes, you know, with the assignments, you know, if they just Google it, they find almost everything. You know, it's a matter of the way we learn has changed completely, and the amount of data that we are generating with the chats and everything. Okay, so I think now that I've given you this vast introduction to what big data, how this big data came into place, what is big data? So how would you define it? Tell me things about big data. If you think of big data, what is the first thing that comes to your mind? Anel?
Facebook.
Facebook, why?
Use this information to provide people this amount of movement you do in internet.
Perfect. What else? Give me an example. What is your name?
Emily.
Emily. Oscar, yeah. What is, well, yeah, don't think. When I say big data, tell me the first thing that comes to your mind.
Yes, I'm also using social media.
Social media, that's a perfect example. You can repeat, by the way. Stefan.
My mobile phone.
Your mobile phone, you're generating data all the time.
And sending it to Google and whoever is watching.
Yeah, any example from that side? Yeah.
Myself.
Yourself?
Yeah.
I mean, tell me why yourself are generating.
When I send it back to how many entities information from just every weekend.
Yeah.
I send it where we are, where I'm parking, where am my visa card.
Exactly.
Where I do today, where am my location.
All that data.
Is data registered and control.
Say again?
And that's provided.
Control. What kind of control?
You can control everything.
You can control everything. This lady here.
I think it's just the masses of data that's collected every day intentionally or unintentionally from normal life
In every aspect. Sometimes we don't realize that even when we pay for a coffee, you know, like with the credit card, something like that, it is amazing, isn't it? Yeah. Do you have any example? You.
I work in health, so I don't really have a big data from, I reckon, is all about the storage.
Yeah.
Like the speed of how much you can use for this storage. Like internet, people will be asking with data, how much data you can use.
Yeah.
It's very basic.
But you say you work from health?
Yeah.
I work from health as well, and we generate a lot of big data. I'm going to show something.
Yeah, when you say you work in New South Wales,
No, New South Wales, University of New South Wales. I used to work for New South Wales, but anyway, I just put some examples here, financial markets, and Stefan knows about these things more than me, I guess. I guess there's a lot of the stock exchange, bank transactions. When I think all the bank transactions that we do in a day, the electricity markets, all the data that is, you know, that the electricity US, all that data that we are generating, social media, and the government and healthcare, because in healthcare we generate, I'm going to put some examples now, I don't know, transport. I think everything with our Opal card is recorded, by the way. So if you go to your Opal card website, it says where you've been, how much money have you spent. How much time do I have left till 10, you said? Okay. Anyway, this is just, so I don't know all of these, by the way, but this is just for you to just pay attention to the zettabyte, the one that is almost the last one. And look how many 0, 0, 0, 0, 0, 0, 0, 0 up there, okay? So it's a big number. Just basically, let's remember this. Okay. So there will be 44 zettabytes of data by this year, in this year. And I read that this is more than the number of stars in the known universe. That is like, wow. And that's just some numbers here that we saw before, like every day, and this is I think in the 2019, but it's even more as we saw before, 500 million of tweets. This is what you were saying, the data that we generate without realizing. This is a 28 petabytes, I think it is, petabyte here, petabyte, of data generated from wearable devices. So my step and all these things. 95 million photos and videos shared on Instagram. This is amazing, just a day. Almost 300 billion emails per day. So this is the kind of data that is being generated every single day. And if we go to the website that we had, this is very, very, this is still going on because I think it's the day in the US, but he said that it will be 500 million. So yesterday I was checking, actually in the evening, I'm going to put it here, before I went to bed. And there were, geez, why all of this? There were 700 million of tweets that day, yesterday. So really, really amazing. Any comment with this?
It depends on Trump. It goes between 500,000 and 1 million.
Yes. Sorry. I go back to the presentation. Yeah. And now that Emily show me how to do this. And how do I do this? Anyway, so just for the share, for the health, and this is the area where I work. There is one thing called electronic medical records. So I told you before that many of the medical records in hospital are still paper-based, but I think in New South Wales we are pretty good and we are moving towards everything being electronic. So we have what we call EMR, or electronic medical record. So whenever you go to the hospital, either you go to ID, you go to the outpatient clinic, or you go to your inpatient, everything is being recorded electronically. So you have from your diagnosis, all the procedures that they do to you in hospital. And when I mean all the procedures, it's all the surgery, if they are healing you a wound, and even if you have a priest, for example, that is praying with you, your family members and your social conditions, how you live, because if they discharge you, they have to know if you have any conditions, anything. All this data is recorded all the time. And even if you're, this is just if you're a normal patient, but if you're in ICU, like, it blows your mind, that's so much data. And ICU has been transferred to electronic not long ago. The amount of drugs that you have, all of that is contained in the electronic medical record. So basically, yeah, this is all the information that we have, the vital signs, and we have allergies, image. How does it look like? Well, if you go there and you put it in a flat table, it will be very boring. So this is just an image of how boring it is. This is a data set that we use in my course, and it's basically like admissions to hospital. We have sex, age, I don't know, this is a US data set, so it's payer code, medical specialty, all the drugs, all the tests that have been done, so you have a lot of data. And this is just something that I wanted to show you in terms of big data in the area of health, and this is what we use to do our research. So basically to do our research, and we understand health not only as I go to the hospital, but we understand health as a holistic thing, you know, like if you interact, for example, with social services, that's something that is happening to you that could impact your health as well. So what we do is that we not only use a data set, but we do what we call linkage. So we link, like for example, I don't know, what's your name there in the back? Jess. So imagine that we are interested in Jess, and then I link all her data sets just to, I don't know, investigate what type of health patterns she has in terms of going to the doctor and things like that. And we do this at a massive scale because we do with Australia. And basically I just put this one from the point that you are not born to the point you die. So the first one that we have is we have some data in Australia of prenatal data from mothers. So we can know if the mother, for example, smokes or attends antenatal care or things like that. Then we have perinatal outcomes. So this data is recorded. So the weight of the baby, if the baby had to be admitted to a special admission or things like that. Then there are many data sets about early childhood development. In this case, for example, I put the example of the ones that are measured at age 5, that this is standardized in New South Wales. We have data for all the family and social services, so all the encounters with social services. So if there is a child concern report, if someone has called the service. We have also the standardized test results that they do at school for age of 8, 10, 12, and 14. We have all the GP visits, and when I say GP visits, it's just an example because really we have the whole Medicare. So every time that you use your Medicare card, we know if you have been to the GP, to the specialist, to you have a blood test done or anything. Same with PBS, or the prescribed medication, so we can know all the medications that you have. If you have any interaction or social housing, interaction with police, that is very important, especially in cases, I don't know, of domestic violence and things like that. It depends on the study, obviously. Interaction with justice and courts, ambulance data, so everything related to ambulance, what happened to you, vital signs when you were there, mental health, especially outpatient, then emergency departments and admissions. Not only the data that I was telling you of the electronic medical record, but also New South Wales and Australian government has what we call routinely data collected. So all these big data sets, emergency and hospitals, as I said, registries. We have many registries in Australia. I put the example of the cancer registry because I worked for a year for the cancer registry of New South Wales. So every single case of cancer that is diagnosed in New South Wales goes to the cancer registry. So you have to report it. So then we have the cancer, your age, the type of cancer, and not even that, the cancer registry, for example, has all the preventative as well. So I used to work for breast screening in New South Wales. So every woman that goes to breast screening in New South Wales is also in the datasets of the cancer registry. I don't know, many other datasets because there are so many that are collected. And then finally, we have the death registry of New South Wales, and we know the cause of death. When I say we, it's we. Everyone with the appropriate ethics applications can access to this data. But basically, it gives you a very good picture of what we can do with this data. And just what I was telling you before about the electronic medical record is just these two little things there. So, but as you can see, there is a pretty good picture of this big data in terms of health. In order to make you feel better, this data is not just available for you. Hackers usually, I mean, this is very highly protected in the area of health. There are many checks and balances. And if you want to leak this data, in this case, us as researchers, we can't do it ourselves. So we have agencies in Australia. In New South Wales, it's called the Centre for Health and Record Linkage, sharing. Or we can also go to the Australian Institute of Health and Welfare. And here I put in red the countries that have similar institutions that do this linkage of health data in the world. And you can see Spain there. I don't know exactly the name, but we have one agency. Okay, let's going to take up some breath. Any question?
You say anyone can have access to this data. It's an application.
Well, I guess, I mean, in my case, because I work for a center for research, but if you pass the ethics committee, for example, in order to access to these big data sets, the ethics committee is New South Wales Population Health that sits actually at the Cancer Institute of New South Wales. You put an application in, and if it is accepted, you can. For the data that the government is collecting as routinely, obviously you pay, by the way, not for free, and you pay a lot of money. But then, for example, now we are working, for example, very closely with RPA. Well, actually, with Sydney local health district, that RPA hospital and Conca hospital are included in the LG. And then this project, just to have the data, is taking us years because you have to establish first a rapport, and then just to extract the data from the electronic medical record takes a lot of time and all the ethics. And I'm going to present a project that we are doing with RPA, and you see how the difficulties of anonymization of the identification and all the little barriers that we have. But allegedly, yes, you could access this data.
You have access to a data with basically faceless code.
Yeah, let's put the example of Jess. So in New South Wales, what we do is probabilistic linkage. So Cheryl knows Jess' name and surname and age and date of birth and her name and surname. And then she's looking for her in all these databases and is doing the linkage for us. And when they give me the data, for me it's not Jess, for me it's number 25. Sorry, Jess. So I don't know anything about her, basically. Another thing is just that when you have this data, you can't disclose any count less than, in our case, is 10. Because if you have a rare disease, if you have something, I don't know, you go to hospital with a very specific case, you can identify people. At the very end, ultimately, you can identify if you really put a lot of effort. But we never disclose counts less than 10, for example. Yeah. And then the power of this big data, if you think about it, just as a fifth. Imagine that you, for example, have a rare disease. Before, it's difficult, to see what you can do. But here you can collect all the data from people from Australia, and somehow you can see what happened with them, what was the treatment. A patient like me, that is called. So then doctors can make an informed decision, or a bit more informed decision than before. Another problem that we have here in Australia was the outcomes, and not only health outcomes of minority groups, like I'm thinking, for example, of Aboriginal people, but we only have 2% of the population in Australia. It's very little. Whereas now, we can collect more data and we can do something, to change this situation. Sorry, Jorge, you were going to ask something.
Yes. How about the privacy? Can you actually opt out of collecting all this data?
No, you can't. Basically, if you have Medicare and if you go to Medicare, everything is collected. And this is what is called, by the way, secondary use of data. The primary use of data is not for us researchers to do research. The primary use usually is billing, is in the case of Medicare is billing. So you go to your GP, you swipe your card, and your GP claims the money to the government. Same with the pharmaceutical benefit scheme and all these things. Then this is de-anonymized and passed to researchers, and this is secondary use of data. But you can't opt out. The only thing you can opt out is what is called my health record. So the Australian government has decided to have a central repository that is called my health record. And for example, all your claims and your hospital discharges, you have the PDF, is uploaded there. You can opt out of that one. But all these data sets is basically data that is collected, and you can't opt out. You cannot.
Is it only the kind of government databases where you have to go to these authorities to do the linkage?
No, all databases.
So if you wanted to do research with some GP practices and a private company, you would have to go to Cheryl to do the linkage, or could you do it with your own software?
You have to apply for ethics.
Yeah.
I think you could do the linkage yourself if you don't apply to these big data sets. But you have to say that you will be anonymized, everything, la la la. So, but yeah, and you have to do it in a way. It's very sensitive, this page. Any other question? Oh, I love this interaction. More, give me more.
Well, I guess you're talking about health, but I guess the Australian Bureau of Statistics collects a lot of data about many things.
Yeah.
Agricultural production, exports.
Yeah.
Can we do the same thing?
Yeah. I particularly don't use much of the data of the Australian Bureau of Statistics, but yeah. When we were, for example, when I used to work for the Cancer Registry, for the Cancer Institute of New South Wales, the Cancer Registry, we used to use the census data and the Australian Bureau. Yeah. But yeah, I mean, I'm speaking of health because it's what I know. But yeah, obviously there are a lot of data collected. Yeah. Now with COVID, you know, all these apps and everything. Imagine. Okay. This is just, you know, also for you to have an idea of how many. This is Medicare. Like whenever we pass our Medicare card, I'm going to show you just one little thing. So you can go to this website, Services Australia. Here, you know, like if we say, for example, from July 2019 to June 2020, how many Medicare categories? And Medicare, remember, is every time you use your Medicare card, the specialist, the GP, the blood test. So how many of these claims or how many of these records we have in Australia? So for this year, in Australia, we have 433 million. So all this. Maybe it's not as big data as tweets, because if you remember, we're generating 700 million of tweets a day. But this is giving us a lot of precious information. And this you have it per state and what kind. I mean, you can drill down because all of these, there are some codes and you can know what these people are doing. So for example, one of our research projects had to do with a type of cancer that is called cancer of unknown primary. So it's a metastatic cancer that you don't know where the primary tumor is. And if you don't know where the primary tumor is, you don't know what type of cells are spreading out. So you don't know what type of chemotherapy or radiotherapy you have to apply. So basically, this cancer is detected very late. So what is happening is that these people go to emergency department and is detected there. Instead of the normal path of detecting cancer or diagnosing cancer, that is GP, specialist, a battery of tests, and then cancer is diagnosed. So we were wondering what is going on, why this is happening. And then we did this study using Medicare claims of why these people, what is going on? Are they interacting with the healthcare system in the same way as others? Or there is something that we don't understand? And basically, we were checking like what is it that we don't understand, and we could see this signal. We could see the signal that they go to emergency and is detected there, but we could see that they go to the doctor as well. That is what puzzled me, you know. So they go to the doctor, but the doctor couldn't identify the symptoms as being cancer. And usually, the pattern of patient was a very fragile patient. That it was already has many comorbidities, was old. And then somehow, you know, like this, it's very difficult, I guess, to be a GP. So we are still trying to untangle what happened there using this data. Okay. So basically, one thing that also I wanted to call your attention is that I showed this data set that it was like an Excel sheet. But basically, 80% of the data that we have nowadays in the world is what we call unstructured data. So we don't have these beautiful records that I'm telling you, okay, you go to the GP and the claim is number 2233. So GP visit at this time, at this date. No, the unstructured data is, what do you think is unstructured data, by the way? Well, I don't have to explain it, and you tell me instead. What do you think is unstructured data? What is your name? Sylvia. Nice name.
Unintended steps.
So structure, I'm going to give you a tip. Structured data is the typical data that you can see in a table, like in an Excel table. That's structured data because it's beautiful in a way. It's columns, rows, you have numbers, or you have categories, and that's easy to analyze.
Is it something that you have to invert from?
Kind of. You're in the right direction. Anyone else? What's your name? Ima. Nice to meet you, Ima.
I would think something that data that doesn't follow any pattern and they're not very relevant or they don't have anything in common. But you're not able to do it.
Yes. So basically, think of a PDF, or think of a letter that or an email that you send. Basically, it's natural language. You say, "Hey, good morning. My name is Ima, or my name is Sylvia. I'm here today at Macquarie, listening to the guy, blah, 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 blah." So in a way, that information is, it's a whole email. That's what we call it an structure because it's not as easy. You can't put it in a cell, or you can, but it would be very big. And I just want to raise the attention that it's not very easy to analyze, and it's 80% of the data that we have. So imagine all the reports that a company has, all the Word documents, all the PDFs, all the pictures or photos that you upload on the Instagram. So all of that, like we have numbers, I can compute an average, I can compute an interval, but if we have thousands of pictures that you have uploaded to the internet, what do they tell me? I mean, this is what is called unstructured data because it's not a structure. It's exactly what you were doing and you were saying and you were saying. So it's a bit more complicated. I wouldn't say a bit. It's much more complicated to analyze. Is that clear? Is this idea of unstructured data? As a certain. Yeah, a video. Exactly, that's unstructured data. Exactly. Because you are analyzing the unstructured data, which is a video, in order to detect something and produce some structure, which is okay, this person has crossed this boundary. That's a perfect example. But I just want to say that as it says, most organizations are making good use of structured data, so basically tables and spreadsheets. But a lot of untapped business critical insights are held in unstructured data. And this is everything that is like resumes, emails, documents, legal reports, voice recordings. That's not so easy to analyze. But this is a lot of potential. I mean, there's a big potential, by the way, if you want to make money. There's a lot of potential because it's untapped. It's not, much of it is not analyzed. So here in structured data, we have what I said to you. It could be displayed in a table. It could be numbers, dates, or just categories. Like, for example, person is healthy, not healthy. And this is 20% of the data, more or less. These are estimations. But unstructured data can't be displayed in tables, like all the videos, images, audio, videos, word processing, emails. Estimated 80% requires more storage. So basically, this is what I was telling you. This is we know a bit, and this is the tip of the iceberg, sorry, but we have a lot of things here that we are not analyzing at the moment. We are starting to analyze. And one of the examples that I'm going to give you is that these child summaries in hospital. There's so much information contained in that, in that document, but it's not easy for the machine to analyze what is going on. And that's why we have to use natural language processing. And I'm going to a project that we are doing in a second. Okay, so I think now we are experts on big data here in this room. So we know that big data has these 5 V's, which is big volume, like huge amounts of data, velocity, because it comes, like I'm updating data all the time that I go to hospital, my tweet account, you this morning when you did your transaction with your visa, so my wearable device. Variety, because I mean, you name it, there's so much variety, especially if it's an structure, we have all these images, audio recordings. But then we have these 2 V's that is quite interesting. The veracity is like, how good quality data we're generating. But good quality is like, sometimes, you know, if I'm doing audio, it could be shit, you know, sorry, pardon my English. So it could be, you know, like not well recorded. And the other one is value. How much value I can extract from that data. In the case, for example, that I was telling you of cancer of a non-primary, well, we are trying to bring something to society, but sometimes there's not much value into what we are doing. But then, you know, so far, I think we have just data. All that I have been telling you is data, 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 data. So basically, what is the purpose of having data? How can we make sense out of it, you know? Because if you have a lot of records, you know, that's fine. It's like, yeah, you know, it's like the Lord of the Rings, my data. I have all this data, but how do we make sense of it? Any suggestion? How? Yeah, perfect. How? I know, but how do we do this process to convert, as you say, data to knowledge? How? Oh, you're having a presentation. Fine, we will discover later. Stay here. Stay tuned. Can I just give a teaser? Yeah.
Allow us to represent the behavior of the system or something.
Yeah.
There's several ways, so that we need to be very careful with that. In just data information,
not good. Exactly.
So you need to do some more development. So okay,
so what is your name? Genaro is going to introduce that. I mean, just you can use statistics, you can do rules, as he was saying. I'm just going to focus in one of the aspects that we can do. And I'm going to talk a bit of artificial intelligence, just because, again, it's what I do, health and artificial intelligence. But there are many things that you, I would say that many of the things depend on the purpose. So you can't use artificial intelligence for everything. It depends on the application and the goal that you have in mind. Because if my goal is to know the average of patients the average age of patients that come to hospital, frankly, I don't need AI. I just need to run, you know, spreadsheet, you know, and say the average. So mind you, with this concept of artificial intelligence, that even if I work on it and a benefit of the coolness is overrated. And one of the examples that I put here that everybody loves is the self-driving car. So we have been speaking of all this data we have, all these sensors and everything. So the self-driving car is a good example of application that is using all this data, all these images of the road, and we are training algorithms for these cars to be driven. So far, we are I think far from having completely self-driving cars. But this, for example, is an application of using data in order to make sense of the world and do something. Basically, the way they do it, and I was reading yesterday, Tesla has all these images, and with all the cars in the world, collect that it has a Tesla car, collect all these images and it's training an algorithm to say, okay, when you see the sign of maximum speed 70, just go, you know, and reduce the speed of to 70. And as you can say, I mean, you show many examples of what you have to do, and you train the algorithm to do that. So another example that I found it fascinating, I don't have any clue of it, by the way, but I saw it yesterday and I said I have to speak about this, is how we can find how the proteins are folded. And basically, you know that everything that we do in our body, proteins usually are part of it. You know, if you flex a muscle, if we attack the virus with our antibodies. So, and what it gives a protein the functionality is the 3D structure that the protein has. So, for example, antibody proteins, they are Y-shaped, and they collect the viruses with this Y shape. But this isn't what I say in green. it would take, I mean, this information of how something is converted in a protein is in the DNA in something that is called amino acid. But just to decode how from these amino acids we are going to have a 3D shape is super complicated. And it says it took longer than the age of the known universe to randomly enumerate all possible configurations of a typical protein before reaching the true 3D structure. But this is done in milliseconds in our body. And what I found, I saw this in, I think it was in a paper on Nature. They are developing algorithms that are capable of predicting from these amino acid codes where will be the 3D shape. I thought, yeah, I thought it was amazing. Okay, this is one of our projects. And this is about what I was telling you about the electronic health record. And then this is people that are in the ICU. And even, you believe it or not, before I started working in this field, I didn't know that there wasn't a consensus in, you know, in what to do when you're an ICU patient. For many of the things, if you have sepsis, if you have, you know, doctors do what they have learned. And even here in Sydney, depends of, you know, if you work in St. George, if you work in RPA, how much antibiotic you apply. And I was in this discussion with doctors, you know, for patients with sepsis, and I said, I never and ever put heparin, I think it was. And then the other doctor, oh, I always give heparin to patients. And I said, wow. I mean, so basically this problem was how we manage hyperglycemia. Hyperglycemia is when you're an ICU patient, and it's very common when you're in hospital that your blood glucose level goes very high. So basically there's no consensus of what to do. And here you can see there are two bands. We can decide choose a threshold, and in this case is 180, and to make the patient have less than 180 milligrams per liter, I think it is, or just to choose a narrow band and make the patient to be in this little, to this narrow band. So what are we doing? But in order to do that as well, we have to predict what is going to happen, because if we want to control the hyperglycemia, and in this case we decided to go with the less than 180 because it's what the doctors told us, you have to predict what is going to be your level of glucose level, because you have to administer the insulin, and also I learned a lot, by the way. You have to, patients have the IV with the parental, which is the fluid, basically. So what kind of fluid they are giving you, so your glucose levels vary. So basically the problem here for my colleague Oshin was to predict what is going to happen in the next 2 hours. So basically what Oshin did, very successfully by the way, is just that you have this information of the patient in the electronic health record or medical record. If it's diabetic, how many days has been in hospital, what happened to that person. And then usually you might or you might not, because this is another thing of the data. We have a lot of empty records. You can have some labs results. So basically we start, the green thing is prediction in 2 hours. So we are starting predicting glucose levels in the next 2 hours, using whatever information we have available. At the beginning, when the patient enters in ICU, we don't have much information. But then as the patient stays more and more in ICU, we have more information. So basically, we're predicting what is going to happen in the next 2 hours. Well, he did this machine learning algorithm. It worked pretty well. So here in black, you have what is the real measure. Let's go into this patient, for example. You have the real measures. And this was, the blue one is the algorithm. And also you have to take into account that the glucose levels is measured sometimes every 2 hours, sometimes every 4 hours, sometimes, you know, it's not continuous. But the algorithm in this case is giving us at each point what it will be the glucose level. So this is very important in order to make an intervention and to say, okay, this level of insulin or that level of insulin, 10 minutes, okay. I'm going to skip this one. This is another colleague is doing this, and this is what I was telling you with Royal Prince Alfred and Concord Hospital. So what we are interested in doing here is that we have all these discharge summaries that contain a lot of information. And I don't know if you know that when you are discharged from hospital, a human being, what we call coder, reads all your discharge summary and goes to all your discharge summary and codes with international code. Where is your principal diagnosis? Where is your secondary diagnosis? So the principal diagnosis is the reason you've been admitted to hospital. Where is your secondary diagnosis? Is you have, I don't know, diabetes, HIV, whatever. All the procedures that have that, like the surgery with this machine, with that machine, because the hospital in New South Wales have to charge the government the money in order to, for these services that are provided to you. So this is super critical because the coders, are very expensive in the sense, and I don't mean expensive money, by the way. It's very difficult to train them because then you have to read that. It's a very boring, well, I shouldn't say that, by the way. But it is very tedious, to read everything. You have to pay attention to detail. You have some help with software. Anyway, my colleague Label is trying to do that automatically. So basically, we are trying to read what is going on or what happened in the discharge summary and come up with this code. But the first thing that we have to do is just to de-anonymize or de-identify, because this project started only 1 year ago. Because all the discharge summaries come with Sylvia, for example, and Inma, and then not only that, but we can see the name of your husband, the name, the doctor that treated you, the address. So basically, we have to, in a way, train the algorithm to find these identities. So these, for example, in this case, this is the real discharge summary. This is not a real one, by the way. But it says Mary. Mary is a 10-week-old female who presented la la la. So basically, the blue ones are names. The yellow ones are dates. So basically, what Lego had to do is to, one by one, go to the discharge summaries, and we did 500, and tag all these names and say, this is a name, this is an identifier, this is an address, this is an email address. So one by one, we tag all of that. And then we teach the algorithm, this is a name, this is blah, blah. So the algorithm learns how to identify what a name is, what an address is. And once you have identified that, you remove it. In this case, for example, you give a random name, Kate Wayne. In our case, we just remove it and we put name, surname, identifier, telephone number. So this is, Label only did name, date of birth, address, phones, and identifier numbers. So basically, 600. He annotated 2 people, by the way, because you have to do this with 2 people because there is always disagreement. So 2 people annotated by hand all the discharge summaries. Then there was a third person, that it was me, resolving conflict. And then we trained the algorithm, we show one, this is a name, blah, blah. And then we tested with something that the algorithm didn't see, to see how well the algorithm did. We were very surprised because Label was very impatient, and when we were having only 50 discharge summaries, the algorithm already learned the pattern that if I say Mr. is a name after the dog. And certain grammatical expressions that they were in the discharge summary, you learn, a doctor name is coming next, or an address is coming next. Things like that. So it was very interesting that with 50 was already very good. And well, I'm not going to show you all of it, but basically this, you have to put it in a format. We did a deep learning model, and this is. So basically, yeah, I think we can finish. I had just a bit more about what is artificial intelligence, and basically, when we think of what is artificial intelligence, we have to define what is intelligence to start with, because it's not very easy to know what is intelligence. And what has happened in the community so far is just that what we understand by intelligence is that it could be either a machine is very good at doing a specific task. Like for example here, the machine is very good at doing discharge summaries, identifying discharge summaries. And this is very good because it's something very tedious for us, and the machine is going to be amazing. And we gave the machine 400 discharge summaries to train, but the world is our oyster. We are continuing, so we are going to give more and more and more. So in some months, the machine is going to be perfect. So the machine is going to be amazing at be identifying these teacher summaries. But don't be fooled by that, because if I put this algorithm, or if I move this algorithm to do another task, let's say, to identify, maybe not in the chat summaries, but in Twitter, for example, the same. I put Twitters and I said, okay, the same algorithm, give me the name, give me everything. Maybe the algorithm is like, what is this? This is not a good chat summary. Probably it's not going to be very good. Again, so whereas a human, like Imam, knows that, this is a name, and if I move here, this is another name. So humans are a bit more versatile. So in the area of interpreting this big amount of data with machine learning or with artificial intelligence, we've been very good at this. And making algorithms that are very good at specializing in tasks, to put it that way. But I think intelligence is a bit more, which is the second one, like how a human could change from one thing to another, in a way, to generalize, to, like, if you are a self-driving car, this is a problem with the self-driving cars, they are learning, for example, with the inches and with everything, to recognize, for example, how to drive with self-driving cars in Denver. I'm putting it as an example. But if you put the same car in Madrid, for example, it doesn't work. It doesn't work at all. And I think, just to finish up, it's just that, I don't have the video here, but I was watching this video of a Tesla car that was, working very well. But what happened, that it was in this motorway, and a truck, tumbled, rolled over, and it was in the middle of the road. You know what the Tesla car did? Yes, straight into the car, into the truck. Wow. And it's like, it's a situation that the algorithm wasn't trained for. And as a human, if you are a human, even if you haven't trained off, your intelligence said, oh, shit, a truck. So and I could see, the other cars slowing down, going to the side, and, turn around, or not turn around, but going around. But the Tesla car went exactly. So this is where we have to be careful with artificial intelligence, because there is this hype of, yes, we can do many things, but this is still very early, and it's a very immature field, and we don't even have the definition of what intelligence is, and what is more importantly, how to measure it. How to measure these algorithms to say that they are doing something that is intelligent. Because at the end of the day, what we want is machines to replicate human intelligence. But for example, what I was telling you of analyzing these hospital discharge summaries, yes, they are very intelligent, and they deal with a lot of information that humans cannot do, because I would be so bored after 5. They're very good at that, but I think I made my point. Did you understand this? I think I'm going to leave it there. Thank you very much for your attention. And what else? Yeah, of course. Questions. Yeah. We have how long for questions?
No, we don't have a long time, but if we want a coffee, and we're going to keep talking there. But I'm going to use the opportunity to see if anyone on the audience as well. We have 20-something people on Zoom, not here. But if anyone has any questions here, might use the micro, which we should have used before. But yeah, we can do it now.
Thank you very much. An amazing presentation. Amazing. I was wondering, do you think this algorithm will replace the GPs?
No.
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 Never.
No, never.
Because they. Okay.
I think they can replace the GP for very, again, trivial things. But in this case, humans have, again, I don't know in 500 years, but there are so many situations that, it's like the Tesla car. There are so many situations that the algorithm is not going to see, even if you train and train and train. So I think, and this is my thing of what we want to do with artificial intelligence, or how we want to make sense of the data, to produce these applications. Do we want to fully replace humans? I don't think this is the case in the case of GPs. I love my GP. I think it will be a decision-making tool. I think it's already there. but I don't think it will replace the GP. It will replace, for example, it will replace these coders that I was telling you in hospital, and I'm really sorry for them. But these coders can be used, these humans can be used for something much more useful, you know, than not just reading these chat summaries. For that, it would be very good to do repetitive tasks that there's so much information, big data that we are saying here. For that, they are good so far, but not to replace humans in that respect. I think this is my personal opinion of everything I have said.
We'll talk in 10 years.
Yeah.
Any other questions? No, I think that everyone is ready for a coffee, maybe. But I can see that in the audience here, there's no questions coming through.
Well,
no, sorry, there is one. So when doing research, how much do we know how to correct for human bias exacerbated by algorithms? Thanks, Miriam.
That is,
No, I'm just saying the name of
that's a super good question. And that's why I think that I haven't gone into this presentation. Human bias. Of course, the data is biased. So if we train an algorithm in, and I'm going to explain this concept. This is something that happened, for example, in the US. They wanted to automatize, to make automatic the decision of some judges. So they didn't have to go into, you know, into the whole records, the electronic health records, but the records to make a decision as a judge. And the algorithm was completely biased because it happened that people from certain minority groups, and I think it was African Americans, the algorithm always said guilty, 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 guilty. So you have to be very careful because if you are training with data that is biased, you are including this bias in the system. So you have to have human knowledge. Again, humans are very important. You have to have human knowledge to make the algorithm learn the way you want the algorithm to learn. Another example was Amazon. They wanted to, because they received so many applications when they opened for a position, they wanted to have this algorithm to just select, to shortlist people. Well, guess what? No women were selected. I don't know how the algorithm did it, you know, but only males were selected. And it was because some of the, I don't know, maybe the information that they had was completely biased. So obviously, you know, there was something wrong. If you take into account, I don't know if it was maternity leave or what they give to the algorithm, but you have to be careful. And you have to do always this exercise. So when you are testing your algorithm, like for example, now with these chart summaries, we go and we test and we see what are the errors, blah, blah, that the algorithm is doing what you want the algorithm to do. Because otherwise you have to restart and you have to rethink the problem. This is something that I haven't said here, but I always tell my students, you know, you have to have your goal very clear from the very beginning, and you have to assess. That's a huge problem in artificial intelligence nowadays. Good question.
It was a good question. I'm not getting any more questions here, so for everyone,
I want to say just two more things.
Yes, we are going to have a break of half an hour. Here we will have coffee, and everyone in the audience, please don't leave us, keep going, because this forum is going to keep going the whole day. But yes, I'm just going to first, you know, say to thanks Oscar for what he's been doing this morning. I think that we've all learned quite a lot. I had to say that I've been listening to a lot of podcasts on big data, but there's a lot of things that I haven't thought about it, and so I've actually learned a number of things this morning. So yeah, well, you would like
I want to say that basically I want to do a bit self-promotion. So at the UNSW, we have the Health Data Science postgraduate degree, and we teach many of these things with big data. So it's Master of Health Data Science, and my course is machine learning and data mining. And also, I wanted to say thank you for inviting me. So thank you very much. I wanted to say thank you to Manel that has inspired me so much to this talk and to many others. So thank you, Manel.